Okay, so let us recall what our general aim has been so far. See, we are trying to look at the set u mod PSL2Z, okay, and in the last few lectures we have proved that u mod PSL2Z is a Riemann surface, okay, and how did we prove that? We proved that by realizing that PSL2Z is a discrete group, and it leaves invariant the upper half plane, so it is a Fuchsian group, and then we proved the result that for a Fuchsian group the notion of discreteness coincides with the notion of being Kleinian, and because it is Kleinian, therefore and in fact we proved that the set of points where the group acts properly discontinuously, namely the region of discontinuity of the group, is certainly contains the invariant half plane or disk, okay. So in this way PSL2Z, just using the fact that PSL2Z is discrete and the fact that PSL2Z is leaving the upper half plane invariant, we are able to conclude that the region of discontinuity for PSL2Z includes the upper half plane, and therefore you are able to divide by the upper half plane and conclude that u mod PSL2Z is certainly a Riemann surface, okay. Now the next part of the story is to try to show that this Riemann surface u mod PSL2Z is actually none other than the complex numbers. So I just want to show that there is a holomorphic isomorphism of u mod PSL2Z with the complex numbers. So to try to understand where this will lead to, okay, let us try to do some heuristic thinking, okay. So you see, basically you have so you have u mod PSL2Z, and so maybe I will put a thickened u to specify that this is the upper half plane, right, and of course u is the set of all complex numbers tau such that imaginary part of tau is positive. This is the upper half plane, and PSL2Z leaves the upper half plane. It is precisely the set of holomorphic automorphisms of the not precisely, in fact it is a subgroup of PSL2R, which is precisely the holomorphic automorphisms of the upper half plane, and we want to prove that this Riemann surface, we have proved that this is this map is a map of Riemann surfaces. It's a holomorphic map, and the quotient is a Riemann surface. We want to show that this Riemann surface is actually biholomorphic, that is holomorphically isomorphic to the complex numbers, okay. So for a moment believe that we have that, okay. What does it mean? See, for that matter, suppose I give you even any function phi into the complex plane, okay. Suppose I give you a function phi from this Riemann surface u mod PSL2Z. This is the set of orbits of PSL2Z in the upper half plane, which has been made into a Riemann surface. Suppose I give you a holomorphic function on this. Suppose I give you a holomorphic function on this. You must realize that if I compose it with this projection, suppose I call this projection as pi, okay. If I compose it with this projection, I get a holomorphic function. Let me call this as phi hat. I get a holomorphic function from the upper half plane to C, because after all this is just composition, this is a holomorphic map, the canonical quotient map is holomorphic because that is the way we constructed the Riemann surface structure on this, okay. And I have assumed that phi is a holomorphic function, so the composition, if I call that as phi hat, okay, then phi hat is also a holomorphic function. So but what kind of a holomorphic function is it? It's a holomorphic function that is going to have the same value on the orbits of PSL2Z in U, okay. So trying to find even a holomorphic function, for that matter even trying to find a set theoretic function on this Riemann surface, okay, is trying to find a function on the upper half plane which is constant on orbits, okay. It has to have the same value on orbits, only then a function on the upper half plane which is constant on orbits, only such a function will go down to define a function on the set of orbits, okay. So you see, so you are trying to look at so in particular if you want a holomorphic function into C, that is a holomorphic map into C, you are trying to look at holomorphic maps from U to C which are constant, which have the same, that is which have the same value on every PSL2Z to Z orbit, okay. So what does this mean? See, let us go back and try to understand what this set U mod PSL2Z was originally, where it came from. So if you remember, what we did was for every tau in the upper half plane we associated the lattice L of tau, okay. This was you can take the lattice spanned by 1 and tau, okay, namely you take all complex numbers of the form n times 1 plus m times tau where n and m are integers, okay. This is a lattice, okay, this is that is, it is an additive subgroup of the complex numbers, and of course in fact it is a Z module, it's a discrete submodule, Z submodule of the complex numbers, okay. This is the lattice, and then if you remember using this lattice we constructed the torus, the complex torus defined by this lattice by simply going C modulo this lattice. So from this we went to C modulo this lattice to get a torus T sub tau. So this T sub tau, it was a complex torus. So if you remember C to C mod L tau, okay. So here when I say C mod L tau, L of tau is elements in this lattice, but I am thinking of them as acting on C by translations. So and of course translations are certainly Mobius transformations. So L of tau is identified with a subgroup of automorphisms, holomorphic automorphisms of C, and then I am just simply going modulo that subgroup, okay. And you know what this is, you know that this is a covering, it is a universal covering, it is a universal covering for this complex torus, alright. And of course the fundamental group of this of the base of this complex torus can be identified with the deck transformation group, which is precisely L of tau, which is isomorphic to L of tau, which is isomorphic to Z cross Z, okay. So we know this. So the point is, for every tau in U we are associating this complex torus, and in fact what we how did we get this U mod PSL2Z? We noted that the complex tori, complex one dimensional tori T tau 1 and T tau 2 are holomorphically isomorphic if and only if tau 1 and tau 2 can be moved by an element of PSL2Z. In fact what we proved was that the set U mod PSL2Z, namely the orbits of PSL2Z in U, is in bijective correspondence with the set of holomorphic isomorphism classes of complex tori, okay. So U mod PSL2Z is let me put this is a bijective correspondence with set with the set of holomorphic isomorphism classes of complex tori. Okay, so this is how we started. This is how we started, and therefore, you see, if I go back to the situation, trying to get hold of a function on u mod PSL2Z is the same as trying to get hold of a function that does not change if you change the equivalence class of the element here under PSL2Z. In other words, it should be something that depends only on the isomorphism class, the holomorphic isomorphism class of the complex torus that is defined by a point above. Okay, so in other words, what is a function like this? A function like this which does not change on orbits is called an invariant. Okay, so of course it is invariant under PSL2Z, but geometrically you can also think of it as trying to produce for every isomorphism class, holomorphic isomorphism class of complex torus, you are trying to produce something which depends only on the holomorphic isomorphism class. Okay, so you must understand that trying to cook up a function like this has got to do with finding invariants. Okay, finding invariants for holomorphic tori, namely quantities, mathematical quantities which depend only on the holomorphic isomorphism class of the torus. Okay, you are trying to find for every complex torus some quantity. Okay, that quantity should be such that if you change the torus by an isomorphic torus, the corresponding quantity should not change. Okay, such quantities are called invariants. Okay, and you are trying to find invariants for tori. So it is obvious that these invariants have got to do with the geometry of this torus. Okay, and in fact they must have something to do with the geometry of all the tori which are in that particular orbit under PSL2Z, namely all the tori which are holomorphically isomorphic. So this leads to trying to look at trying to study these tori themselves. So well, if you go back to the famous ideas of Felix Klein, so he somehow thought that geometry of a space has to be dictated by the functions on the space. Okay, somehow if you know all the functions on your space, then you should know the geometry on the space, and you can turn this around and say that you can dictate a geometry on the space by specifying the kind of functions that you are allowing on the space. And in a way this is we can see this already in trying to say that if you want to study differentiable manifolds, you take the allowed functions to be C-infinity functions. If you want to study complex manifolds, you take the allowed functions to be holomorphic functions. Well, if you want to study algebraic manifolds, you take the allowed functions to be locally rational functions, quotients of polynomials. Okay, so if you go by that, then I would like to look at functions on this. Okay, and since this is certainly a Riemann surface, okay, I would like to look at let us say holomorphic functions on this. So what I would do is well, I will try to look for functions on the torus. Okay, you try to look for functions on the torus, and then one hopes that you try to find a function that depends only on the isomorphism class, the holomorphic isomorphism class of the torus, and then you have found an invariant. Okay, and finding such invariants will precisely try to give you functions from this set, okay, into whatever set. Okay, for example, trying to show that there is an isomorphism phi of this set with C. Okay, let us say I want to show even that there is a bijection of this with C. Suppose I just want to show that, leave alone holomorphic isomorphism, suppose I just want to show that there is a bijection of this with C. then what I should do is for every whole isomorphism class, holomorphic isomorphism class of a torus, I have to produce for you one complex number, and actually you can produce one such number that is called the j-invariant of the torus, okay, and we will see that, okay. So but the point I am trying to say is that trying to look for invariants like this leads you to try naturally to look at functions on the torus, okay. Now well, you see, so you see, suppose I look at a function on the torus, suppose I look at a function, let me call this as f. Let's assume that you are looking at a complex, suppose you are looking at a complex valued function, and let's be optimistic and let's assume that, well, the best thing to assume is that f is analytic, okay. So suppose f is analytic. So I am searching for functions on the torus, okay, and suppose I have a function like this which is analytic. Well, let me call this projection as pi sub tau, not to be confused with this pi, okay. So well, I can compose like this, so I put a circular arrow saying that this arrow is this followed by this, that's what it means here also, this arrow is this followed by this, that is what the circular arrow means, okay, namely that the diagram commutes. So well, you can see that if this is analytic or holomorphic, then this is holomorphic, okay, but this is not going to give us anything. That is because you see this guy here is compact, this torus topologically is compact, alright, because you know basically it is the image of the fundamental parallelogram formed by the fundamental parallelogram, the grid formed by 1 and tau, okay. So actually what is happening here is that if you remember, see I have 1 here and I have tau there, okay, and then you know there is a parallelogram like this, okay, and if I repeat this parallelogram to form a grid, the points of the grid are precisely the points of this lattice, so the points of the grid are precisely the lattice, okay, and you know that the image of this whole parallelogram along with the boundary surjects onto the torus, okay, and this is of course compact, it is closed and bounded, and therefore the torus is also compact because this map is continuous, after all you have given it the quotient topology, alright. So this is compact, therefore and of course a holomorphic map is continuous, therefore the image of this set in C is going to be a compact subset of C, in particular it is going to be bounded, therefore this map, this holomorphic map will be an entire function which is bounded and then it has to be constant, so we are not going to get anything. So the moral of the story is trying to look for analytic functions on the torus is not going to help, okay. So what does it mean? It means you have to allow singularities, okay, it means that you have to allow singularities, right. So let me write that here, this means f has to be constant, so of little help, okay. So we have to allow f to be to have singularities, okay. You must allow functions to have singularities, alright. So well, you know if what are the singularities, possible singularities of an analytic function? Well, you know there are isolated singularities and there are non-isolated singularities, and among the isolated singularities there are the removable singularities which are actually not singularities, okay. Then there are the poles and then there are the essential singularities, okay. So if you want the mildest type of singularities, what you would do is that you would like to have at least poles, okay, and trying to study analytic functions which have only poles, and if you also ensure that these poles are isolated leads to study of what are called as meromorphic functions, okay. So the simplest kind of functions you can try to think of on the torus are going to be meromorphic functions. Okay, so the mildest possible singularities are the poles. The mildest possible singularities are poles, and so we look for meromorphic functions f on the torus. You look for meromorphic functions. What are meromorphic functions? Meromorphic functions are functions which are analytic at all points except for a subset of isolated points where this function has only poles. Okay, and well, so you are looking at meromorphic functions, all right, and notice that and therefore what is it that I can do is, well, I can have a discrete subset and I can have poles at each point with certain multiplicities, but even in that the simplest thing I could have is pole only at one point. Okay, so of them you take a pole at only one point, for example, alright. So well, so we could look at meromorphic functions with pole at only one point, or let us say pole at a few points to begin with, alright. Now what I want you to understand is what does looking at such a function mean above in the complex plane. So you see, suppose I have an f which is meromorphic, and well, so if it is a meromorphic function, it is not defined at the poles. So in principle when I draw this arrow, this is not really a map from this to this, this is a map only from this into C union infinity, because at poles the function will take the value infinity. Okay, so you know I'll just so the best way to put it is well, let me put C union infinity, okay, and then write it as holomorphic. Okay, so you know meromorphic functions into meromorphic functions, complex valued functions, are precisely the holomorphic functions into C union infinity, because what happens is at the poles you define the function value to be infinity, okay, and then you get holomorphic functions into P1, the Riemann sphere. Okay, so this is C union infinity, the extended complex plane, which is identified with the Riemann sphere by the stereographic projection. It is a Riemann surface, and then a holomorphic map into that is the same as giving a meromorphic function otherwise. Okay, and the poles will be all the inverse image of the point at infinity. Okay, so mind you, I am looking at meromorphic functions on the torus. Okay, now what is it above? What is it that is happening above? So you see, the first thing is that suppose I assume that there are suppose I assume that the poles are isolated. Okay, then if I go all the way above and look at this function f hat, okay, then this function f hat will also be a meromorphic function. The only thing is that the poles will just, it will have infinitely many poles, and what will happen is if f has a pole here, okay, the inverse image of that pole, it will be an inverse, it will be a point which will be spread over a grid, and that grid will be translates of this grid. Okay, and it will have poles at all those points. Okay, and what is so what you get is looking at a meromorphic function on the torus is same as looking at a meromorphic function on C. Okay, and further notice that if this function f hat has to be invariant under the action of translations by elements of this lattice. So you see f hat of z plus n times 1 plus m times tau must be equal to f hat of z for all z that is not a pole for f hat. Okay, this should happen, okay, because after all these 2 points are going to be identified when you by this map by this projection by this map, because this point is a translate of that by this element, that's an element of the lattice, and that's the that is the group of translations by which you are modding out. Okay, so this function f has to satisfy this condition. Now you know, see what does it tell you? What it tells you is that it tells you that f hat has to be a doubly periodic function with periods 1 and tau. Okay, so f hat has to be a doubly periodic function with periods 1 and tau. Okay, so what is the moral of the story? The moral of the story is the simplest kind of functions you can try to write on the torus are going to be doubly periodic meromorphic functions, and these are precisely what are called as elliptic functions, and were studied first by Weierstrass, who gave a decent beautiful theory for these functions, and it is through these functions that you completely understand the geometry of the tori and everything that is connected with tori right from number theory to algebraic geometry is done by looking at the meromorphic functions. Okay, so up to this point our discussion has told us that you know actually you should look at doubly periodic meromorphic functions on C, namely elliptic functions on C, they are called elliptic functions, and with periods 1 and tau, alright. So well let's look at the properties of such a function. See such functions such doubly periodic meromorphic functions are called elliptic functions. They are called elliptic functions, and why they are called elliptic functions is because they help to actually prove that this Riemann surface, this complex torus, can be thought of as zeros of an algebraic equation, and in fact it turns out to be an algebraic curve, okay, and that curve is called an elliptic curve, and that is the reason why they are called elliptic functions. Okay, so I will come to that later on. I will come to that later on because it is a deep fact that every complex one dimensional torus of this form is actually an algebraic is given by zeros of algebraic equations, okay, and in fact it is a much more deeper theorem that you take any Riemann surface, you put the topological condition that the Riemann surface is compact, then amazingly the Riemann surface, this compact Riemann surface becomes can be thought of as zeros of an algebraic function, so it becomes completely algebraic. Okay, so it is the demonstration of that fact for the case of complex tori can be achieved by using the elliptic functions. Okay, so Weierstrass studied a particular case of elliptic functions which are called the so called famous Weierstrass phi function. So I will explain to you how this Weierstrass phi function is motivated. Okay, so well we have to look at elliptic functions, alright. Now what are the kind of functions that we can look at? So of course you have to decide, let us take at least one point or a couple of points and try to and let us decide that the function has poles at those points, but before that I want to make a remark. So you see here is a remark. If I calculate, so you know I take, so here is my, so let me draw a small diagram. So you see I have, so here is my torus, okay. So so here is my torus, and you know, and what is above is the complex plane, and this is the projection, this is t tau, okay. See, suppose I take say a couple of points, okay, a finite set of points separated from each other, and take their inverse image. Well, you know, there is this grid of on the complex plane, there is this lattice which corresponds to 1 and tau. So I have this lattice here, this is the fundamental parallelogram whose image is here, okay. And if I take the image of such points, the inverse image, well, if the inverse image is, if you look at inverse images, if an inverse image is going to lie inside this parallelogram in the interior, then it's going to be only one. But it could happen that, you know, it could lie on the boundary, in which case you will get 2, and if it is one of the vertices you will get all the 4, okay. So what I am trying to say is that since there are only finitely many points, okay, so let me call these points as say p1, p2, etc. up to, let us say, pn, okay. Then what I can do is, well, I can translate this grid in such a way that, you know, I can translate this grid in such a way that all these inverse images of these points, I have only one representative inside that grid. I can translate it, okay. So I can move it, if some point tries to come at the vertex I can avoid it, so I can translate this. So in other words, what I can do is, you know, well, it may happen that, well, p1 is inside, p2 is inside, maybe for p1 I can find a unique representative, for p2 maybe I can find a unique representative because it is inside, but maybe for p3 I might get 2 representatives, one here and one on this, one exactly in the opposite edge of the parallelogram, so it will be some p3 prime hat, okay. And then maybe pn might have all the 4 vertices as inverse images, it could happen, alright. But, well, the point is I can move this this parallelogram a little bit by translating it, so that all the representatives that are come into the interior of the parallelogram, and all the representatives are already there. So, you know, I can actually choose an A such that, you know, if I take A, I can choose a complex number, I'm trying to think of them as vectors, well, I can choose a complex number A such that, you know, if I now draw this parallelogram, if I translate it by this A, okay, then what I will get is I will get A, I will get A plus 1, then I will get well, A plus 1 plus tau, then here I will get A plus tau, I will get this parallelogram, which is just a translate of that. But I can choose A in such a way that I get exactly one representative for each point in this, lying inside in the interior. I can do this, okay. So choose an A such that this translated parallelogram has exactly one representative from each of these things. And let's call this this bound, let us give an orientation to the boundary of this parallelogram so that it becomes a closed path, okay, so that it becomes a closed path, and then try to look at the integral 1 by 2 pi I integral over well, I mean, if I call this rectangle as I mean this parallelogram as A B C D, if I take the path integral over A B C D of this function which is above, which is f hat of z dz, if I look at this, what will I get? well, you know, by the residue theorem I should get the sum of the residues at each of the points inside where the function has poles. Okay, so what I will get is I will get summation I equal to 1 to n residue of f hat of z at the point pi hat. This is what I will get, this is the residue theorem. But you see, the point is that f hat is periodic, is doubly periodic, therefore the integral of f hat from a to b will cancel with the integral of f hat from c to d, because after all the f values here are the same as the f values here, because tau is a period. Okay, and the integral of f from b to c will cancel with the integral of f from d to a, that is because 1 is also a period for the function. See, in the definition of the periodic function I could have taken m equal to 0. What it tells is that f of z plus 1 is also f of z. Okay, and I could have put n equal to 0 and I will get f of z plus tau is also f of z. Points here differ from corresponding points there by tau, and points here differ from corresponding points here by 1, therefore all the integrals will cancel, so this is going to be 0. So the moral of the story is the sum of the residues at these poles is going to be 0. What does that tell you? That tells you that to begin with you cannot have a single pole which is a simple pole. Okay, because suppose there is only one pole, I mean the simplest thing is that I would like to have only one point where there is a pole, and the simplest kind of pole I can think of is a simple pole. I can try that is the simplest I can try, but that won't work because then it will tell you the residue at that pole is at the simple pole is 0. Okay, that cannot be. Okay, so what is the moral of the story? The moral of the story is that you must have if you take only one point you must have a pole of at least order 2, or you should at least choose 2 points with simple poles. Okay, so there are 2 choices you can make to at the simplest, trying to study the simplest meromorphic functions. Either you can choose a single pole and make it order 2, or you can choose 2 poles and of order 1. In any case you must have sum of residues at both the poles must be 0. Okay, so what Weierstrass did is that he chose a single pole of order 2. Okay, and so what we do is, well, we look at this probably this line does not look so very straight. Let me draw another so that it looks a little decent. Okay, so what we will do is we will do the following thing. We will take this lattice. I mean, so we go back to our so let me write the conclusion here. This implies we cannot f cannot have a simple pole. This can't happen. All right. So we take this. So here is my lattice. So this is 1, this is tau, this is 1 plus tau. It's complex plane, and well, here is my torus t tau. Okay, and we are following Weierstrass, trying to get hold of trying to study meromorphic functions having a double pole at one point below. Okay, so and what is at one point? We may as well choose that one point to be the image of this whole grid. So this whole grid goes to some point here. Okay, because all of them are equivalent under the translations of the lattice. So if all the points of the grid are going to be mapped to a single point, okay, that point you can look at that point. Okay, and well, I can so in particular it is that point is the image of 0. Okay, that point is the image of 0, so I will call that point as pi tau of 0. It is also pi tau of any point of the lattice. Okay, and I am trying to study I am trying to study a function defined on the torus, I am trying to study a function defined on the torus which is meromorphic with a double pole which means a pole of order 2 at that point pi tau of 0. Okay, this is what I am going to study, and well that means that the function above f hat is going to be an elliptic function, a meromorphic doubly periodic function which is going to have a double pole at every point of this lattice. It is going to have a pole of order 2 at every point, because you know if this function has a pole here, then this function above will have a pole at every point which is the inverse of this point. Okay, so your f hat will be a doubly periodic function which will have, you expect it to have a double pole at every point of the lattice. Okay, what kind of function would it look like? Try to guess. See, you can write well, you can just take 1 by I can take if you know if I take a point of the lattice, it looks in the form n times 1 plus m times tau. Okay, and if I write 1 by z minus n times 1 plus m times tau, this will give me a pole of order 1 at n times 1 plus m times tau. Okay, but if I want a pole of order 2, I cannot have a simple pole at one point. Okay, I need to have a double pole from what I said here. So if I want to have a pole of order 2, I put square, alright, and then this this gives me a pole of order 2 at this lattice point. Okay, but then I want this to happen at every lattice point, alright. So what I do is I sum this over n comma m integers, but of course I should not let n comma m equal to 0 comma 0. Well, I'd rather well n comma m can be 0 comma 0 also, I mean that's not a big deal. I'll get 1 by z squared, I'll get a pole of order 2 at the origin, that's all fine. But then so you know this summation becomes just summation. If I write it as omega in the lattice 1 by z minus omega the whole square, this is what the summation becomes. Okay, now there is a problem. I'll tell you why. See, this is 1 by I can write as 1 by z squared. I'll separate the pole at the origin, alright. So I'll write it as sigma omega belonging to the lattice minus the origin, okay, 1 by z minus omega the whole square. So all I have done is I have just removed the pole at the origin. Now you see, of course I have written down some series here, and of course there are questions of convergence, right. Now as z tends to omega, alright, of course if I fix a particular omega and I let z to tend to omega, then of course this is going to go to infinity, that it should, because it is a pole. But then you see I get the term 1 by omega squared, okay, and you do not want for reasons of convergence, what you do is that you take away that 1 by omega squared. So what you do is put minus so let me write that separately. So this is exactly due to Weierstrass. So you have the Weierstrass phi function, phi tau of z is 1 by z squared plus sigma omega not a non-zero element of the lattice defined by tau belonging to L tau minus 0 of 1 by z minus omega the whole squared minus 1 by omega squared. Okay, now this minus 1 by omega squared is plugged in, so that as z tends to omega, the contribution 1 by omega squared that comes from this term gets cancelled with the contribution minus 1 by omega squared that comes from the other term. Okay, and it is there for convergence purposes, alright. So this is the so called So in fact there is a bracket here, so the summation is common to both of these guys, and this is the Weierstrass phi function. So this is how the Weierstrass theory of elliptic functions starts. Okay, this is how it begins, and it goes on to give beautiful results about tori, which are connected with complex geometry, algebraic geometry, number theory, and so on. Okay, so this is the motivation for studying the Weierstrass phi function. All right. Now, of course, one needs to check that whatever one has written down here heuristically is actually something that makes sense. You cannot simply write a series and expect it to be a function. You have to check that it converges. You have to check that it is really a meromorphic function. You have to check that it is a meromorphic function that converges, namely it is analytic at the points where you expect it to be analytic, namely it is analytic at every point different from any point of the lattice, and you must also make sure that it is doubly periodic, and you must also make sure that the only poles of this function are at the lattice points and the poles are of order 2. I mean, nothing is clear, I mean everything has to be proved. So but the point is that one is able to arrive at the phi function in this way heuristically. Okay, and then it is a matter of some analysis to prove that one is indeed right. Okay, so I think in the forthcoming lectures, therefore what I will do is I will show that this phi function indeed has all the properties, and we will see that this phi function actually characterizes the torus. So by that I mean if you take two non holomorphically isomorphic tori, the phi functions you get, they will not be compatible with each other. Okay, you will get different phi functions. So this phi function kind of distinguishes. Okay, and this is the starting point of trying to find an invariant for tori. Okay, and which is what we are trying to search for. We are trying to find a complex invariant for every isomorphism, holomorphic isomorphism class of torus. Okay, so this is the starting point. Okay, so we will continue in the forthcoming lectures.